Now,
Good.
that's perfect, is it? Good.
100%. Yes,
Good.
thank you.
Well, I will say it's a great pleasure to be talking to you. In fact, I am actually talking to you from Cape Town, so I'm sorry that we're not having a physical meeting because it would have been lovely to meet all of you. Anyway, hopefully we'll be able to get through what we wanted to do, whether we're face to face or online. So the story of the James Webb for me started on Christmas Day 2021 when the telescope was finally launched from the French Guiana from their space center with one of their Ariane rockets. And the Ariane has proved to be an extremely good launch vehicle because it has achieved a high degree of precision, most recently launching a mission to Jupiter, and in this case, launching the James Webb, so that the minimum amount of fuel was used by the spacecraft to achieve its location, which means that, as we will see, the James Webb has enough fuel to keep going for the next 20 years or so. Okay, well, the obvious thing that springs to mind is the comparison between the Hubble Space Telescope and the James Webb Telescope. And, well, Hubble is named, the Hubble Telescope is named after the astronomer that discovered the Hubble-Lemaitre law, establishing the expansion of the universe. And James Webb was a NASA administrator from 61 to 68. And I must say, when I first heard that a telescope was going to be named after an administrator, I was somewhat appalled. But when I heard that James Webb was the person responsible for pointing out to NASA that if it was to have a future, then it could not just focus on manned human launch vehicles. It must branch out into scientific research. And so actually without him, there'd probably be no James Webb Telescope today. Well, quick compare and contrast. The Hubble orbits the Earth, the James Webb orbits the Sun. The Hubble has a 2.4 meter mirror. With the James Webb, you have 7 times the collecting area for half the total upfront mass. With the Hubble, it largely works in the optical region, though it does go out to the near infrared. The James Webb is designed to work exclusively in the infrared. The Hubble was serviceable, as we learned, as saved the whole project. The James Webb is not serviceable because it's a million miles from Earth. And so we're very fortunate that it actually works because there's no chance of fixing it. Okay, if we think about what astronomers set out to do, then essentially, if we want to understand the universe we live in, we have to study it at all possible wavelengths. The shorter the wavelength, the higher energy of the features that we look at, whether it's the sun or going out to the even hotter regions around black holes and so, with typically higher temperatures. When we go into the infrared and the microwave, we look at the cooler aspects of the universe. And we can also penetrate the dust and gas that surround so many things like newborn stars and so on. So the Hubble focused essentially on the visible light, the James Webb on the infrared. And of course, there is one huge advantage of the infrared, and that is when we study the deep universe, when we look far back in time, then the things that we are looking at may have had their origins in the visible or even in the ultraviolet, but they have been strongly redshifted by the expansion of the universe, as we will see. Now, the concept of the what started off as the next generation space telescope, the James Webb, goes back to soon after the actual launch of the Hubble telescope in 1990. By 1996, there was a group set up under Dressler to produce a report about the next generation of space telescope. And it was recognized at that stage that this would have to be complementary to the Hubble, and that certainly it would have to work in the infrared if we were to study the earliest eras of the universe. Then essentially the contract was founded, the mirror size was reduced in about 2003 or so, and with a proposed launch date around about 2010. And of course, things then took a lot longer, as they often do, and it wasn't until 2021 the telescope was launched. And of course, all this time, the Hubble is still operating. We hope that the telescope is initially designed just to last for 6 years, but it certainly has enough fuel to keep it going for about 20 years. Now, I guess those of you who have been involved with large projects will be familiar with the cost creep, and the project started off at a cost of $1 billion. By the time it was launched, it had cost $10 billion. The launch date was another thing that progressed. Launch date moved forward almost at the speed of time. Here we have the speed of time, if you like, the blue line here. Unfortunately, the two curves did finally intersect on the 25th of December, 2021. I've never been involved in the details of a satellite mission, but it must be take an extraordinary toll on one's mental capacities with these costs and delays. But this is a fairly typical situation. The telescope is large, and I think this model gives you some idea of the scale size of the telescope. It has to fit, and it has to fit inside the nose cone of the Ariane launch vehicle, and this meant that we had to have a fold-up design mirror. As you can see, it's made up of individual panels, and the whole telescope has to fold up to fit in the nose cone of the Ariane. Now, I don't intend to go through this in all its gruesome detail, but the launch was just the start of this mission of nearly 1 million miles beyond the orbit of the Earth to its position at the Lagrangian point out here. And during the next 2 weeks of nail-biting activity, various deployments took place. The mirror, essentially the sun shields unfolded, the mirrors unfolded, the secondary mirror and its mountings were deployed. And if I tell you there are 344 potential single-point failures, then you can imagine what a nerve-wracking time this was. A single-point failure simply means that if one aspect, if one of these things here had failed to happen, then the mission was totally compromised. There were no sort of half measures of using it in a degraded state. And to our amazement and excitement, the whole mission, the whole thing did deploy, and it got into its stable orbit. Now, just very briefly, the Lagrangian you can think of, there are various Lagrangian points associated with the sun and the Earth's gravitational field. And the easiest way to think about this Lagrangian point is that the sun and the Earth's gravitational pull combine on this point, and so an object that is at this metastable point will orbit the sun in exactly the same length of time as the Earth takes to orbit the sun. If the Earth wasn't there, an object further away from the Earth would take longer to go around the sun. The actual path, it actually orbits this point here, and the destabilizing forces, well, they're forces that there's a potential dip here, and the forces will drive it out of that position. So it has to use its rockets in order to stabilize itself, keep itself in that region. There we have the relative sizes of the two mirrors, and you will see one is a single block and the other is a composite, and there's a picture of the telescope. Now, the main mirror is one of the essential parts, of course. It consists of 18 segments of gold-plated beryllium, and it has a focal length, an overall focal length, effective focal length of 131 meters. You can see it's quite a fast optical system with a secondary mirror and a tertiary mirror, and then this fine steering mirror here, and the focal surfaces back here. So it means that you would have an image of the moon would be about a meter across. Now, it is figured in the form of a parabola, and there is a recipe that means that the individual segments here are figured to 3 different recipes. This recipe, this one, and this one here. So they have slightly different figures. And as I said, they're gold-plated. There's about 48 grams of gold on them. And the key to their operation is that they are independently mounted on a back frame, and each mirror has 6 actuators that can control the detailed position of the mirror and push it forward, bring it back, tilt it, tip it, and so on. And then an extra central actuator that can pull or push on the center of the mirror to alter its overall figure slightly. And you'll see here, this is beryllium, which is a difficult material to machine, and beryllium and gold-plated, and we've got edge sensing along the sides. Now, almost as miraculous, in my opinion, as the mirrors themselves is the support mechanism. And it's probably easier. It looks a bit complicated here. If we just look at the outside here, we have the outside mirror supports. You can see 3 mirrors supported here. So you can imagine this system folding down. And then if you look here, here is the secondary mirror, and you can see it has a pivot point here and here, and you can imagine the whole thing unfolding and folding out. So this system is actually built of a graphite composite with titanium and invar joints and joint places here. And to my mind, as I said, the miracle of this is almost equal to the miracle of the figuring of the mirrors, in that this whole structure has to cool down to about minus 250 degrees. It's obviously built at room temperature, and it has to be stable to the orders of tens of nanometers. This is the precision we need in order to maintain the figure of the telescope. Now, when it was first launched, of course, each of the mirrors formed its own image here, and these are the 2 wings. And if you put your eye at one of these foci here and look back at the telescope, you'd see one segment of the telescope illuminated. So the first thing was actually to bring all these images so that each image corresponded to its own mirror. And then we had to bring the mirrors into focus. And you can see that procedure here. You'll notice this mirror, bottom right, is not of quite the same precision as the other. Now, when they'd been brought into best focus, they then had to be brought into coincidence. And this is the image of a fairly bright star with all the images in coincidence. But of course, at this stage, we only have the resolution equivalent to the diameter of one segment, because what we then have to do is fine-tune the relative positions of the mirrors to less than the wavelength of light in order that the a whole mirror acts coherently, and then this was the final image. It's difficult. You can't judge the power point spread function here if you want to see the quality of the typical image size. You have to look at the smallest images here. But what was so exciting about this first image was that despite this being a star that you could probably see with a pair of binoculars, you will see that the field of view is full of background galaxies. Now, one of the early sort of shocks in the whole procedure was the fact that within a couple of months, one of the mirrors here had been struck by a meteorite, a tiny meteorite. And this was a much bigger, in fact, it did the equivalent damage that we would anticipate the total impact damage to be over a period of about six years or more. And this happened within a couple of months. Well, the good news is that no further impacts of this magnitude or anything like that size have taken place, and that it was possible to change the figure by using those central actuators and so on to get rid of the consequences of this impact. What happens is there is a wavefront sensor mounted in the telescope effectively that every few days checks the coherent alignment of the individual mirrors. And if you, look here or here, you will see that some of these mirrors don't quite have the same precision as the other ones. Now, to operate the telescope, it must be kept as cool as possible, and this is achieved by passive cooling and by protecting the telescope end from the sun and the radiation of the moon and the Earth with this sun shield. And this proved to be one of the most tricky elements to get this thing to ensure that it was actually going to deploy, and eventually a series of motors and pulleys were used to make sure it deployed. The simple idea is that it doesn't conduct, that the radiation that travels from one surface to the next is reflected and radiates out the side, so that very little energy will make its way through the sun shield. And here we have typical situation of the telescope in orbit. You will see it always travels with its back facing the sun and the Earth. This is the advantage of the Lagrangian point, that both the Earth and the moon are sources of infrared radiation as well as the sun. And by sitting at that point, it can maintain its back to them. And so that the hot side gets up to a temperature of 85 centigrade, 300 degrees absolute or so, and passively the cool side cools down to minus 233. Now, at any one time, the telescope can only observe over this angular annulus of sky, but of course, as it sweeps around the sun with the Earth, then of course the whole sky becomes visible to the telescope. So if we look at the hot side, we see the star trackers, the antenna, and this momentum flap, which I will mention later, and the solar panels. So this is all on the hot side. And while we're looking at the hot side, we'll just look, since I wanted to talk a bit about the telescope itself as well as the results. It has two wide field cameras that look at a 16-degree area of sky so that it can decide where it's pointing. And so that gives you a sort of course pointing. And then once you can use, the instruments inside the telescope for the fine pointing and so on and so forth. The orientation of the telescope is also monitored by 6 hemispherical resonator gyros that are solid state devices. And the telescope can be moved around by 6 reaction wheels. So it's a matter of accelerating or decelerating, and the action and reaction, the telescope moving in the opposite direction. Now, momentum management is very important. There are really two sources of momentum. The results of moving the telescope around the sky. You can slowly accelerate the reaction wheels, and you have to dump that. And this is dumped by firing the rockets and decelerating the wheels. And this can be done every few days as necessary, and takes a few hours of operation. So the other source of momentum is the pressure of solar radiation on this surface here. And there is a little flap like a sail that balances that torque. But of course, this also builds up and has to be disposed of in the same fashion. So the instrument package is all on the cool side and consists of principally, well, 4 groups of instruments, some of which we will have a look at in more detail. And each of these instruments has its own focal plane. Unlike a conventional telescope where everybody observes all instruments look on axis, these have their own fields of view. And this does mean that you can make serendipitous observations with some of the other instruments while, say, you are making a required observation with, say, this particular middle infrared camera over here. So I just want to look very briefly at a few of these things, and the near infrared imager and slitless spectrograph. Let's look at that. Now, you will see the optical systems of all these are really quite complicated. This comes off the fine steering mirror, which gives us the finest control of the positioning of the telescope. Each has its own as its focal plane. Then we have a collimator, so that we send essentially a parallel beam through these filter wheels here. We have 2 filter wheels, and one can have a selection of transmission filters, and the other wheel contains, among other things, transmission filters, but these grisms, which are slightly deviating prisms that are also grating dispersers. So you can select, say, a relatively narrow band transmitting filter here, and you can select the grism here, and this will be the result you seek. A field of view where every single star in the field of view produces a short spectrum, and this enables you to look and examine and look for at a large number of potential objects. You'll see fixed little spots here, which will be the 0-order images of one of the little spectra. So they're dotted around. And to give you an example of this application, here is the grism field of view of this image here, and you'll see some emission lines in this bit of spectrum, some other emission lines here, and by measuring their redshift, we can see that these 2 gravitationally lensed arcs are actually the same object, and that's lensed because they've got the same redshift. So I just now want to look briefly at the near-infrared spectrograph, which also has an interesting feature. You're used to the idea of a spectrograph having a single slit on which you place the object you want to get the spectrum. This thing has a series of what are called micro shutters. So here's the micro shutter mount, and the micro shutter consists of 4 panels, and you see the magnified here and magnified again here, little doors that can be opened, 250,000 of them. And the idea is that you can select out of a crowded field of stars which stars you want to observe by opening the appropriate door that is where the star is in the focal plane. So you run a magnet over them to open all the doors. You then apply an electrostatic current to keep this door firmly open, while the magnet then runs across and closes the doors. And here is a typical array of somewhat higher dispersion spectra, and by judiciously selecting which doors you open and which you close, you can get a large number of spectra and at the same time ensure they don't overlap. And then, of course, you can repeat the same field with another selection of doors. So, and here, finally, lastly, the mid-infrared instrument is the only instrument that is actively cooled. It cools down to a temperature of 7 degrees. The rest of the telescopes operating at about 30 degrees above absolute zero. This instrument is cooled down with a closed cycle cooling system using helium to about 7 degrees above absolute. And you can see its wavelength, its filters range out to 25 microns or so. So we have a very close, how can I say, a large number of filters that cover with the various instruments, the entire wavelength range we're interested in. All the instruments have the same imaging facility, spectroscopy, and, coronagraphic imaging is when you block out the bright star and look at things nearby. Now, we can start looking at results. Here we are looking at a field of view with the Sloan Digital Sky Survey, which goes pretty deep into the sky, conventional ground-based telescope. And there is probably a galaxy there. And when we look, this is now 32 hours of exposure with the James Webb. We just see that the picture field is absolutely chock-a-block with galaxies. They far outnumber the stars. So just to have a look at some results, these are just fun things, really. This is Saturn looking very different from the way we usually see it. The dark surface, we think, is because of the absorption by ammonia, by methane, not ammonia. And here, one of the interesting results is this moon of Saturn. There you can see Saturn in the ring, called Enceladus, and the Cassini spacecraft showed that Enceladus is emitting jets of water or water gas, whatever you like to call it, from its surface. And the James Webb has shown that there is a very large plume of water vapor associated with Enceladus that appears to form a torus right around Saturn. So that was something new. Well, Uranus, we knew, the rings of Uranus were actually observed by Joe Cholmes at the SAO, and he could have been famous, but he didn't quite get round to looking at his data soon enough. They were discovered in the 70s with the James Webb. They look pretty conspicuous, as does we see the rings around Neptune and Triton, which is very bright and in some ways looks like rather similar to Pluto. Now, one of the interesting results that has come out is associated with a few of the many, nearly 5,500 planets that we have confirmed that are orbiting stars near us in our own galaxy. And this particular planet is, let me just explain this graph, actually. This is distance, it's logarithmic distance of the planet from its star. So 1 corresponds to 1 astronomical unit, the distance of the Earth. And this is the mass of the planet in terms of Earth masses. So here we have one Earth mass, 10 Earth masses, and so on. Jupiter about 300 Earth masses. solar system down here. I don't want to discuss this in any more detail, but just to draw your attention to this object, which is somewhat, it's referred to as a hot Jupiter. It's somewhat lower mass than Jupiter, and it's considerably closer. It's less than a tenth of an astronomical unit from its companion star. So it has a much hotter atmosphere. Now, these planets are observed by the fact that they transit in front of the ones in that diagram, in front of their star. So symbolically, here I've shown the planet blocking out about 2% of the light of the star, and I've shown its atmosphere, which blocks out a variable amount of starlight, depending exactly which wavelength you look at the planet-star combination. So thinking of the combined white light, here is 1 or 100%, the brightness of the star without the planet. Here, the planet starts to cross the star, and as it crosses the star, the light of the star drops by about 2% or so, and then climbs back up. But if we now look at the spectrum, so we follow the transit through a spectrograph, and then if you look carefully, you will see some horizontal bands here corresponding to the different molecules that are present in the atmosphere. So here we're blocking out more light because it's a little bit darker, so we're a little bit lower down here because the atmosphere is less transmitting. And that information can then be turned into a spectrum that is upside down, because this is blockage. So strong absorption corresponds to a peak here, in other words, strong blockage, and we see the molecules CO2, SO2, and carbon monoxide. The interesting thing, and there's a lot of work on equilibria amongst gases, is the presence of SO2, which can only be explained by some chemistry that's going on within the atmosphere. Now, this time last week, there was a press release about this object, K218b, from the Institute of Astronomy. This is an object that is referred to as, well, it's not a rocky, it's referred to as a Neptune-like object, probably has a much higher proportion of water and ice than the Earth, but it is within its habitable zone. Although it's at only a tenth of an astronomical unit away, it is orbiting around an M dwarf, a much cooler star than the Sun. So it is at a place where water could be a liquid, and it certainly has sufficient gravity to do that. And this was the press release from Madhu Husadan, who works at the Institute of Astronomy, and he detected methane. Now, methane is observed in our own solar system, but this was the first detection of methane outside the solar system, around an exoplanet. And this referred to as DMS, dimethyl sulfides, which are thought to be, certainly within the Earth's atmosphere, a potential marker of potential life. Now, apparently the interesting thing about this spectrum, and again from molecular equilibria calculations, is the absence of ammonia, NH3, and apparently to have methane without ammonia is a potential indicator that this planet, this object, may have a liquid water surface. So it may become an ocean-covered planet. And clearly, where we have a situation like this, there's certainly the potential for life. So this is one of those watch this space situations. And we can certainly hope there'll be many more observations of planetary atmospheres. Okay, we're now going to visit the Orion Nebula and just zoom in, as it were, on these regions. This is this region viewed with the Hubble Space Telescope. This is the same region viewed with the James Webb over a range of wavelengths. And we want to zoom in on this region here. And when we finally do, we notice this particular feature here, which is a protoplanetary disk. It is a planetary system in the process of growing. It has this disk that is blocking out the light of the growing sun in the middle, and it is from this disk that planets will emerge. Now, these are not new. They were seen with the Hubble, and they are observed in the microwave with the ALMA telescope. But the interesting thing here was this to discover this cation CH3+, which is fundamental in much organic chemistry. And this is certainly a first observation again of this ionized, free radical, I suppose you would call it. Other examples that are not are beautifully shown here. Another protoplanetary disk here with this halo, this teardrop halo formed by the stellar wind and developing a shock front of the material that is leaving this forming planetary system. Let's move on quickly. This is a large area of sky, the Rho Fuci complex, and of Starbirth, a region quite about half the distance to the Orion Nebula, about 500 light years away, a current star formation with these very dark clouds of dust and gas. And then we just zoom in on this area here to see this rather beautiful James Webb image. Bright star here, this whiteness, and this is the way colors are assigned to a whole series of filters showing the presence of dust, the red corresponding to the hydrogen molecule. And here, and these are referred to, this is a Herbig-Haro object, as is this here, these jets emerging from a region where a star is forming here. And we see jets and shock fronts, and you'll see this cone, dark cone here, shadow cone, produced by a disk around a star that is forming out of the cloud. And we see another example of this around this protostellar system here with the disk in the center and the gas flowing out from the protostar in these two open cones. Another example of what's called a Herbig-Haro object, and perhaps the most beautiful one here, HH211, a Herbig-Haro object. These are a few, maybe tens of light years in length, and we see shock fronts developing. When we have a disk material falling from a disk onto an object, we often develop jets that move out in opposite directions, and that's what we're seeing here. So this is the situation that would have prevailed when the sun was forming 4,500 million years ago. Now, moving on to galaxies, this is M74, a typical galaxy with 100,000 million stars in it, regions in these spiral arms of dark absorption, where there are regions of dust and gas out of which stars are forming in these bright clumps here. And when we look at this with the longer wavelength filters on the James Webb, the stars disappear, and we are essentially left with the dark clouds of gas and that now appear to be radiating at these longer wavelengths. And by looking at the wide range of filters that can be selected, we can decide which molecules are present in these clouds. Here's just another example, a region where there isn't quite so much star formation going on, but I draw your attention to the fairly broad brush, fairly clear spiral arms there. And this image looks qualitatively quite different from the previous one. The spiral arms are by no means as obvious. If you look at this, I've drawn freehand some lines where the arms are, and you see how that looks when laid on top of the other. Rather a poor correlation. We see these radial features seem to be much more conspicuous. Okay, I now want to move on to things a little bit deeper and more exciting. And the field of gravitational lensing is certainly benefiting from the James Webb. And just to give you the basics of gravitational lensing, light leaving this object in all directions is deflected by the distribution of mass in this foreground cluster of galaxies. So by the time the ray enters the eye here, we think the object is up here. So just to show you, this is a field rich in these radial arcs of gravitational lensed images. You'll see the image is absolutely full of it, and you see a rather unusual bit of lensing here. And if we just look at that in a bit more detail, this is a lensed galaxy seen with the James Webb in comparison with the Hubble, and we see another feature here with these bright spots corresponding to individual objects that have been lensed and the intensity magnified. Now, I just want to look briefly at this particular, we've gone the wrong way. We've just looked at that one. I want to look at this feature here. This is another field rich in lensing. Look at this linear structure here, and this rather strange, looks like mirror imaged galaxy here. And now we'll look very briefly at this object here. And I just want to say something about lensing and what you can do with gravitational lensing. So if we think of the mass distribution here, then this deflects the light in the way a lens refracts the light, and you can map back to the object plane, which is where the background galaxies are. And depending on the mass distribution here, you can draw these caustic curves, two caustics here, and they map in a certain way into the image plane, where we have what are called critical curves here. And the behavior of an object as it crosses, as it moves through these caustics here in the image plane, that's what we see, this is what exists back here, is quite complex. If we just look at this object that's in the center here, then this one object will produce 1, 2, 3, 4, 5 objects in the image plane. Look at this object, which is on the edge of the caustic, and you will see that it forms a very large elongated object here and has counterparts here and here. So by looking in the image plane and identifying which objects correspond to each other, which you can do by measuring their redshifts, you can, in principle, reconstruct the mass distribution in the imaging cluster of galaxies. And then once you've done that, you can then reproduce the caustics and the critical curves, and you can reconstruct the image that you see here into its original form here. So that's what they have. Kamiensky and Fry have done this in July of this year. These two are the principal lensing galaxies. So you take out the light of those, and then these are the caustics that have been drawn on the basis of the duplicity of various images in here. And then we can iterate this model until we get a satisfactory agreement between what we observe in the sky and the distribution of the caustics, and we can reproduce the original imaged object here. Now, why would we want to do this? Well, not only does the gravitational lens increase the scale of the object and allow us to see structures that we wouldn't otherwise see, but it also increases the brightness, which might be from a factor of a few up to a factor of 1,000 or more. And what this is revealing is a very young a galaxy, very low mass galaxy, actually, much less than the Large Magellanic Cloud, maybe only a few, maybe 10 times the mass of a globular cluster, in which at this stage there is a lot of star formation taking place. So that is something that can be done. Another rather interesting aspect of gravitational lensing is the situation here. We have 3 images, and it's all a bit messed up. There's a foreground star here, these 3 images, and they're 3 images of this galaxy. Here's one image, there's the other, and there's the 3rd image, and there's another interfering star. But the interesting thing is this image shows a supernova, one of the type 1a supernovae used for distance measurement, but we have the chance to see the follow the light curve of this object as it fades now, magnified by oh yes, I haven't actually got the magnification here, but by quite a large amount, so that we can observe one of these objects when the galaxy was about 30% of its present age. Now, from, again, knowing the model of the mass distribution here, you can work out that this is an image of the galaxy 1,000 days earlier, and this 300 days earlier. So we have the chance in the future to observe the whole of this light curve of this supernova, because it'll eventually, well, it'll first appear here, and then it'll appear up here. Now, a lot of the work of the James Webb is being done looking in 2 regions of the sky corresponding to the Hubble ultra-deep fields, north and south, also referred to as Jade's fields, because other deep observations have been made in this area. And although the telescope can look at the entire sky, obviously, if we can focus on areas that are already explored, then this is a very good way of following up on existing observations. So this is just to give you some idea of the scale of the fields in relation to the moon. Now, just seeing the field here on the screen, well, it doesn't necessarily look that impressive. So to give you a feeling of how impressive it is, how deep it goes, we're just going to look at one tiny region of the sky. And of course, the things that we tend to be interested in are the very, very faintest objects, the very faintest, in particular, faint red objects, little red objects. Now, before I go any further, I want to give us a very quick, how can I say, review of a few aspects of what we know about our universe. And we go back to Hubble, who showed that the universe is expanding and that the spectra of distant galaxies are redshifted, and that redshift is proportional to distance. And we can easily measure that redshift. We just compare the wavelength of the light that we observe with that which was at which wavelength it was emitted. And we know from our laboratory physics that if we see sodium light in a galaxy, then it would have had the same rest wavelength as it does in our laboratory at home. So, and we define this Z, which is, if you like, delta lambda over lambda, which for small velocities, for nearby objects, we can relate to an expansion speed related to V over C. Now, the nature of expansion, of uniform expansion, is to look like this. And all this are two overhead transparencies, one with random dots and the other one produced by enlarging it by a few percent. And you will see if we coincide the dots here, all the other dots seem to be moving away from it. And if we select another point, all the other objects seem to be now moving away from this point. And this is the nature of uniform expansion. Now, when Hubble made his observations, and subsequently we could calibrate the rate of expansion by looking at a nearby cluster of galaxies, measuring their distance and measuring their speed of the expansion away from us, their redshift. Redshift 0.0005, and so they're going at 1,500 kilometers a second, and they're about 60 million light years away. So if this were two views of our universe from that observation, and in fact, these dots could be just dots on a screen, but they correspond to the size of the universe at two occasions, 263 million years apart, using the Hubble calibration that we've just done. And of course, this could be just markers in space-time, a few feet apart, but of course we'd have to make these observations deep in space, far between clusters of galaxies without any stray gravitational fields to distort things. And we can turn that into a map by just arbitrarily deciding, it's on the scale of the map, by deciding this circle will be 263 million light years in diameter. Then it could be a map of galaxies. And because of the finite speed of light, we don't get the overall bird's eye view of the universe. We see all galaxies inside this circle when they were younger than 263 million years, ones on the circle when they're 263 million years, and ones out here when they were much, much older, 500 million years, and so on and so forth. And this is the way we see our universe. Now, the point about Z, and the reason that I've gone through all this, is that in practice now, Z can be far greater than 1. And that, you might think, implies that the velocity, we're looking at velocities greater than the speed of light. And in a sense, we certainly are, because we're looking at the expansion of space, expansion of space-time, not the movement of objects relative to each other. So what Z tells us is how much the wavelength of light has changed since it was emitted. And this, in turn, tells us that the difference in the size of the galaxy today, the size of the universe today, sorry, not galaxy, galaxies don't change in size, divide over the size of the universe when the light was emitted. So that is 1 plus Z equals the observed wavelength over the emitted wavelength. So we are now going to go into the realm when we are looking at values of Z greater than 10, which is something unimaginable a few years ago. Now, we did relate Z to time when we made that little scale drawing, but if we want to relate Z to times in the early universe, then we have to have a model of how the expansion changed with time. And we're not going to go into that, but it depends on things like dark energy and the amount of dark matter and so on and so forth. So we need a model. And when we have a model with those parameters up there, this is how Z changes with time. And you can see that for a Z of 20, the universe was only 200 million years old. At the Z of 10, it was, getting on for 500, 600 million years old, and so on and so forth. And of course, for Z plus 1, Z equals 0, is the universe is 14,000 million years old. So you can see Z is related to age, and we are going to be looking back into these ages. Now, I don't want to go into this in any great detail because we're going to run out of time, but when Z was 1,000, then the distance between things was 1,000, but the density went as 1 plus Z cubed, so the density was 1,000 million times greater. And when was Z 1,000? Well, round about the time of the microwave background. Now we have to prepare ourselves with a short summary of the evolution of the universe before we move on to the final bits of this. The Big Bang, well, we're not going to go into that. We're going to take up the story when the universe was about 300-something thousand years old, when it cooled to a temperature of about 3,000 degrees. The electrons got together with the protons and the helium nuclei, and we had a lot of neutral gas, and the photons could now travel in straight lines through the neutral gas. Then, and you will see age up here and redshift, as we call it, or Z plus 1 down here, just to give you the calibrations. This was a time when the very first stars, when mass was getting together, but there were no stars, nothing to be seen with the naked eye. The universe was expanding and cooling. And then, when the universe was a few million years old, redshift from 20s, maybe, the very first stars came to life, and as they did, their ultraviolet light started to re-ionize the gas. And you might say, okay, if the light couldn't pass through ionized gas here, how come it can pass through ionized gas here? Well, you just have to go from your 20 cubed compared with 1,000 cubed, and you will see we're talking about a millionth or so of the density of ions here, so they were no longer totally scattering the photons. So this period of reionization is a very important period early in the history of the universe, and one that is being probed by the James Webb. We want to know, when did it take place? It was very important, not only on the way it distorted our view of the earliest bits of the universe, but also on the way galaxies could grow, because this gas was very much hotter than the gas back here, and this has governed the way maybe low mass galaxies can accumulate mass and grow in size. So it's very important to know exactly what was going on at this time. So there we have the basic story there. And one of the first challenges that the James Webb has taken up is discovering more about this period of reionization. And I've drawn it symbolically here. The stars start, well, I didn't draw it, this is from the Webb. Stars are being born in the central regions and eating out the halo, reionizing the neutral gas. Now, light of photons of longer wavelength than H alpha, long wavelength photons, can easily travel through this neutral gas. After all, we see the microwave background, so no problem. So we would see the longer wavelength spectrum of these stars, but finally, when the gas was completely reionized, we would see the shorter wavelength radiation, because the shorter wavelength is no longer being mopped up by the neutral hydrogen. So this is the situation. So the hydrogen is ionized here, and the high energy photons are less absorbed. And this manifests itself in the spectra of these objects, where we see a sudden drop off in the ultraviolet short of Lyman alpha here, where essentially there was predicted to be a dip where the very last masses of the neutral hydrogen were taking out every single photon of the shorter wavelength. And then, of course, these are lower redshift Lyman alpha regions that are picking up the bits of neutral gas that's still here. And of course, when gas clouds collapse to form stars, there's plenty of neutral gas that hydrogen forms, the molecule again, when it's protected from ultraviolet light. So indeed, when we started looking at spectra from the James Webb, we could see this important Gunn-Peterson trough as it's observed. And one of the, let's move on because we're a bit running out of time. Let us now look at some of the exciting, back to the Jades field, some of the mysterious red dots. And here is a particular example of a not particularly red, but a reddish dot. And here is a more dramatic example of one known as GN-Z11, a particularly unusual red dot that actually was first observed by the Hubble Space Telescope. But with the James Webb, we could get this absolutely exquisite spectrum of an object with a Z equals 10.6. So a universe was 11 times smaller than it is today when this object was emitting its light. Now we can do even better that this object has been observed recently and looked at by Maialino and a group, and they noticed they can measure the line widths. These lines we see, we're quite familiar with these in active galaxies that we see much closer to home, and they have deduced that this object is in fact an active galaxy, a galaxy with an active black hole at its center when the universe was only about 400 million years old. Let's now look at this as another cluster that is responsible for gravitational lensing. So it's having a magnifying effect of objects within this field here, and you can see some dramatic examples of a lensing there. Let's now focus on this bit of it here. This is cluster Abel 2744. It's about 3,000 million light years away, but we're looking at objects that are more like 13,000 million light years away. And if we enlarge that object and you look in the box here, you'll see a little red dot. Here you'll see a red dot, and here you'll see another one. These are all the same object, gravitationally lensed, and they are named QSO 1A, 1B, 1C, and they have a redshift of 7.5. But interestingly enough, here we have an extended normal galaxy, 3 images of it, and that has, from the spectrum, a redshift of 9.7. So what we found is another example of an active galaxy and an example of a normal galaxy. There they are. And we're going to look quickly at the last example, UHZ-1. And we come back to this particular field and we focus in on this object here. And there it is. There is another little red object. And when we get a spectrum of that, we can, this is again with the James Webb, we can see it has a redshift of 10 or so. And it also has what looks like a evidence for an active black hole at its center. And this is further confirmed by the observations of the X-ray satellite, Chandra, and you'll see the whole of that Abel field there to be compared with the Chandra X-ray imaging here, but that can be done at the mapping can be done at a very high precision. So we can see in that little box some pixels here corresponding to X radiation coming from this particular object, again confirming its black hole status. Now we can make estimates of the mass of the black holes, and there they are at this very high redshift. And this is the result from Lino's paper. And the thing, don't worry about the pretty curves and so on here. Rather look at the scales. We've got redshift along the bottom here, and we've got black hole mass, which is judged from the breadths of absorption lines and the emissivity of the X-rays. And you will see that we have, this is 1 million. So this object has a mass, a black hole of more than 1 million solar masses, this more than 10 million, and so on, up to 1,000 million. And the other thing that has been going on in recent years is that these redshifts, which only correspond to are still less than 1,000 million years old, we found a large number of objects with black hole masses at their centers of up to 1,000 million solar masses. Now, many people have, well, not many, but a lot of people have suggested that the whole of cosmology must undergo a rethink. How is it possible that when the universe is only 400 million years old, we could already have 1 million solar mass black holes? And just as a quick resume of black holes, these are quasars, these are galaxies with 1,000 million solar mass black holes at their centers, where the emission from the material falling onto the black hole completely outshines the surrounding galaxy. And there we have a symbolic black hole, artist drawing, and the jets that develop above it and the accretion disk. So this is the sort of thing we are thinking about, and we have already got these within the 400 million years of the universe. Now, there is another group, Martin Rees is one of them, and so I suppose the axis of the Institute of Astronomy is around this, who have been thinking about these problems for some years and see no problem with the idea of forming massive black holes so early in the history of the universe. And the two methods that they were thinking of was that the first generation of stars might have formed, would have formed high mass stars of maybe 100 solar masses or so, that might have formed dense clusters. These stars would have evolved into neutron stars in a few million years or so. The neutron stars would collide and merge to form massive 100 million solar mass black holes. Now, the other idea, which is a much more dramatic idea, is called the direct collapse black holes. Now, these are not quite direct collapse. They, instead of forming 100 solar mass stars, they form 20,000 solar mass stars that evolve very quickly and then would form black holes. And these would then continue to accrete gas and possibly merge to form these 100 million solar mass black holes at such an early stage. So those were the two paths, and it was thought unlikely. These things are extraordinary objects. So it was, people speculated as to how this could be. Now, don't worry, I'm going to finish. I know I'm running over time a little bit, but I am going to finish fairly soon. But I, again, just want to say something very quickly and generalized to give you the appropriate background. This you may recognize as the microwave background. One of the successes of modern cosmology is our ability to predict from this as the starting point, these density fluctuations of 1 part in 100,000, we can predict the cluster, the structure of the universe that we see around us today, this foam-like structure, this clustering of galaxies, 1,000 million light years here. So these are large-scale structures. And when we look at a region like that, in this is observed. This is how this sort of structure will look in our models. Now, what we are seeing here are halos out of which clusters of stars and galaxies will form. This is where dark matter is drawing matter in to these points along these streamers. This is the structure that emerges in this model, largely driven by galaxies, by gravity, and clusters of galaxies will emerge here. And here is a tiny detail of a particular type of structure where we have material flowing in 4 different directions. And so Latif was able to take one of these structures and then evolve it and show how he could produce these massive collections of gas that were able to form very large mass stars. Now, what is special about this is that normally, once gravity collapses something, it heats up, and then as it cools, it is able to fragment. So in order to prevent an object fragmenting, in order to let it create very large, massive objects, we have to stop it fragmenting. Now, the problem with hydrogen is, as soon as when it's hot, it cannot radiate away its heat unless it's very hot, because it has to radiate things like Lyman alpha and hydrogen alpha. But if it can form a molecule, then it radiates very easily at very low temperature. So one way of avoiding that is by having these streamers creating this turbulence. So turbulence is like a proxy for temperature. It effectively stops the gas cooling. And what he found in his models was that at this enormous redshift, when the universe is only 124 million years old, he was producing objects that had 20 or 30,000 solar masses and had not fragmented, and therefore were going to actually collapse into stars. So this is an idea that's been around for a while, that has been demonstrated in a model. And just to summarize here in this diagram, at this age, at this redshift, these halos, these collections of gas, maybe 500,000 solar masses of gas, start to form. The halo starts to contract under gravity, and it now weighs maybe 20 million solar masses, and stars form within this. They form black holes of 20,000 solar masses, and then these accrete and have no problem in forming these 1,000 million solar mass black holes at these kind of redshifts and ages. So although we have some pretty amazing objects there, it looks as though theory and observation are slowly beginning to coincide. And just to jump to the very final point, well, almost final point, the record holder for redshift at the moment is this object here, and it has a redshift of 13. So the universe is 14 times smaller. It was only 300 million years old. There it is. And there's its rather crude spectrum. And that's where it lies in our diagram. So we're now excitedly probing back to the time when the very first stars were forming in the universe for the very first time. And this is where the James Webb is taking us. And I would just like to end up with this last result, well, not really result, but summary that came out last July, where they characterized the science and performance after, at the end of commissioning in July. It has 1,379 authors, so I can bet my bottom dollar they didn't all read it, otherwise they'd never have got it published in such short order. And one of the summaries is the James Webb is the product of the efforts of approximately 20,000 people in an international team. And as it starts its performance, the observatory exceeds its pre-launch performance expectations, which is pretty amazing. And we can look forward to some very exciting results in the future. Well, I will apologize for overrunning somewhat, and I will stop speaking now. Thank you very much. And
thank you very much, Robin.
Shall I stop sharing? Is that the strategy now?
Yes, you can stop sharing.
Right. I will, and we can take. I mean, I'm happy to deal with questions.
Yes, we ran already quite a lot of over time. I can allow a couple of questions, maybe, if people are still interested to stay around for. Are there any questions?
There's Hartmut. I see his hand up.
Oh, yeah,
Yes, hello, Robin. I haven't seen you in a long time. That I've aged a lot more than you have. Very nice talk, as I'm used from you. The one thing that was intriguing me a bit was that supernova in that gravitational lens. I'm just wondering what one might be able to all deduce from that. Given, is this perhaps the furthest supernova ever observed? Given that
yes, it's certainly further away than the supernovae that we use to calibrate the accelerated expansion of the universe. What one might hope from a detailed study of its light curve, and I don't know if there are any prospects of spectra here, is to see whether it is quantitatively the same as the nearby calibrating supernovae of similar type. As you probably know, there's always this issue of what effects have evolution had, where supernovae of that type in the early universe or earlier universe in any way different? Are there any systematics there? So yes, so it is hoped that some detailed comparison can be made. Yeah.
Okay, thanks.
Thank you. Any further questions? I personally find it amazing that you can, on such an enormous distance, still do these measurements of individual molecules that you can detect, like the carbon disulfide, or the dimethyl sulfide, etc.
Yes, those distances are only hundreds of light years rather than thousands of millions, but they're still, yes, it is exciting. The complexity of the models, of the equilibrium models of those molecules is something that I must say rather awes me, because you have to feed in the atmospheric structure as well. And in fact, I wonder just, and you have to worry about clouds. And you even have to worry about sunspots on the surface of the stars. But all that, you know, if you read the paper, it gets mixed in and worked out.
Well, thank you very much for a very fascinating talk. The only thing that rests me is to thank you, and I want to invite everybody who's here for the next webinar, which will be held on the 18th of October, and will be given by Bruce Henderson on fascinating discoveries of coelacanths of the KZN South Coast.
Thank you.
Thank you very much, and enjoy the rest of your evening.
Thank you. Bye.
Bye-bye.
Bye.